Hello, welcome to the fourth session on Boolean algebra. We have one major topic, and that is the three basic Boolean operations. But in order to facilitate that discussion, we will talk about propositions and axioms, the complement, negation, truth tables, followed by the three basic operations and the order in which we do them. The session has 10 slides and it will take about 16 minutes to complete. Before we get started on Boolean operations, let's talk about the concept of axioms. But before we can do that, we need to know what a proposition is. A proposition is a proclamation or statement which is either only or always true, or it is always false. So it may not be variable. A proposition is not variable. In every case, it is either true or it is in every case false. Now, an axiom is a proposition that is true. So it is a statement that is always true. We can use axioms to build an entire theory of math. They are sort of the foundational pieces of math. And since axioms can be shown empirically to be true, every axiom is sort of fundamentally known to be true. It's either with a simple proof or some other obvious way. Then we know that everything based on these axioms is valid. Now, an identity or tautology is a proposition with an equal sign in it. So an identity may be an axiom or a proposition, or maybe neither. But it equates whatever's on the left side to what's on the right side. It basically says we have two ways of saying the same thing and they are equal. Now let's look at some examples. First, the grass is green. Is this a proposition? The answer is no. And the reason for that is that grass is not always green. It may also be yellow or some other color. So it's not a proposition, therefore it's not an axiom either. The second statement looks a little bit similar. The moon is made of cheese. However, regardless of what the moon is made of, may have different composition. We know for sure that it's not cheese. So this is always false. Therefore, this is a proposition, but it's not an axiom because it's false. The last statement is all three. It is an identity axiom. So it's a proposition that's true. We'll consider natural or real numbers here. 2 plus 2 is 4 is a statement that is always true. It's also an identity because it has an equal sign equating something on the left to the right. And it's always true. So we have an identity axiom in the last statement. There are just three basic Boolean operations, and every other Boolean operation or function can be written as an expression containing nothing but these three. Technically, only two are strictly necessary, but we generally use these three basic operations. And these are the three listed on the slide here, starting with the unary not operation, or negation, indicated by this angle-looking symbol. Binary and, a wedge symbol pointing up. I always remember it looks like an A without the A for and, without the stripe in the wedge. And then the binary or operation, or the wedge pointing down. And other operations like XOR can be written in terms of these three basic operations. Let's start with the first of the three basic Boolean operations, and that is negation, Boolean negation. And let's remember the concept of the universal set that we defined in the first session and the complement of the set. We remember that the universal set is a set of all elements in the context of the study, and in this case that is the Boolean domain, and it only has two elements, the numbers 0 and 1 in it. The complement of a set, the complement of some subset of our universal set, some subset X, is the set of elements in the universal set that are not members of the set X. With that in mind, we can now look at unary negation. This is a unary map, so we're mapping from the Boolean domain back to the Boolean domain, and element X in the Boolean domain is mapped to an output element Y also in the Boolean domain. Therefore, the function is a subset of the Cartesian product of B with itself. It is a subset of this Cartesian product, and it actually is equal to the two ordered pairs shown in the slide. So the not operation is equal to these two ordered pairs we see here. 0 maps to 1 and 1 maps to 0. So negation is called the logical complement, because if we look at the number 0 and we look at the elements in S that are not 0, we only have one element there, and that's the element 1. And for 1, the complement element or the complement set is the set containing just the number 0 in it. So negation is also called the logical complement. Now, before we go on to the AND and OR operations, let's introduce the concept of truth tables, a very convenient way of doing proofs in Boolean algebra, or in fact algebra of finite sets. So a truth table is simply a complete list of all the possibilities of a particular function or operation. It's nothing but a list of all the options. So for a Boolean function, we write the domain of the function, the set of all possible inputs of the function on the left, and on the right we write the outputs of the function. So we literally can describe the function completely with a truth table. And we will see the relationship between a truth table and the Cartesian set product in the next slide. But for now, any function can be described, any function on a finite set, an operation on a finite set, can be described by a truth table where the number of rows in the truth table is exactly equal to the number of input options. So for a unary function on the Boolean domain with two input options, the truth table has 2 rows. And for a binary Boolean function, there are 2 inputs, so there are 2 times 2 options. There are 4 rows in the truth table. In the case of a binary function, each one of those rows corresponds to an input, which is an element of the Cartesian product of the Boolean domain with itself. And the cardinality of the set of ordered pairs resulting from the Boolean domain with itself is 2 times 2. So there are 4 options in the truth table of a Boolean binary function. We'll see more of this in the next slide. Continuing on with our concept of truth tables and the Cartesian product, let's look at an example binary function on the Boolean domain. So we consider the function where the inputs are ordered pairs that are elements of the Cartesian product of the Boolean domain with itself, and each of these inputs maps to an output element that is also a member or an element of the Boolean domain. So inputs are the ordered pairs x, y in the Cartesian product of B. Therefore, the function is a subset of the Cartesian triple product, the product of the set of all pairs times the output, which is again the Boolean domain, that gives us the triple product of B. The truth table simply lists the output that is obtained from each of the possible inputs. So we see here on the left the inputs that are elements of B squared, and they're all listed here. There's each of the possible elements x, y, where x and y can both be either 0 or 1. So there are 4 possible inputs. So we have the entire function listed in this truth table. And for each of the inputs, we have on the right side the output of the function. We don't know what the function is here, but this can be any binary function on the Boolean domain, and it will always have just these 4 rows in the truth table. Now, armed with our knowledge of truth tables, we are well prepared to discuss the Boolean AND operation, also called conjunction. This is a binary operation denoted by the wedge symbol that we discussed. So its inputs are ordered pairs in B squared, and they map, each one of these maps to an output element in B. Therefore, the AND operation is a subset of the triple product, as we discussed. And in fact, it is the set shown here. Let's look at the definition in the box in the middle of the slide here. The output of the AND operation is common truth in both inputs. In other words, if both inputs are true or 1, the output is true or 1. So if only one of the inputs is true, or they're both false, then the output is 0 or false. Note that I use 0 or false interchangeably and 1 or true interchangeably. They're just the same thing said differently. So our truth table is listed here. 0 and 0 equals 0. We have 0 and 1, as was said. One of these is not true, so that's 0, and 1 and 0 is also 0. The only one that produces a 1 is 1 and 1. And the actual set is written out above the gray box here. So we can summarize the whole thing by saying that if A and B equals 1, then it must be that both A and B are true, or 1. Now, the last of our basic Boolean operations is the Boolean OR operation, denoted by this down-pointing wedge. This is again a binary function that takes two inputs and maps each of these pairs to an output element in B. The output of OR is truth in either input, so it's also called a disjunction. If either operand is a 1 or true, then the output is 1 or true. The truth table here is listed below the gray box, so 0 or 0, in this case neither is true, is false or 0, and 0 or 1 or 0, or 1 or 1, each produce true or 1 as output. The last topic for this session is the order of Boolean operations, and this needs to apply when we have a sequence of operations without parentheses. So when we encounter a sequence of operations, we always do unary negation first, followed by AND and OR operations, and then followed by any other Boolean operation. In the example here, we have A or not B and C. So we have to carry out the not B first, no matter what. And then it doesn't matter if we do not B and C first, or we do A or not B first. We'll get the same result. So if we don't see parentheses, we must always carry out the negation, unary negation, before we do other Boolean operations, followed by the AND and OR operations, and then any other. Let's spend a minute reviewing the topics that we discussed in this session. We started with propositions and axioms. We saw that an axiom is a true proposition, and that we can use axioms to build a mathematical theory from basic true elements. Then we started talking about the three basic Boolean operations: negation, the AND operation, and the OR operation. We saw that negation is essentially the same thing as the set complement. We then started talking about truth tables, and we saw this is just a list of all the options, essentially, of a Boolean problem. So a Boolean function, a truth table for a Boolean function, lists all the inputs with the corresponding outputs. And we saw how this relates to the Cartesian product, the other way to define a function. And we then last talked about the order of Boolean operations. And that summarizes this session.